welcome everybody. I'm just going to start off with a slight introduction from myself. This is obviously an IO Associates run meetup event with myself, Sam as well, Jordan and Charlotte. And this is the first of the C++ series. So as you're all aware, we've reached out to you all because the market has sort of demanded it. IO Associates are, host to a number of other successful meetups that we run, including the .NET and Java meetups. And then the C++ network have just asked for this event and we provided. So I just wanted to say thank you again to, all our confirmed speakers, John, Klaus and Allan. Your content looks great. And thanks for sharing your expertise. I think what we'll do now is, start off with John. So John will be talking about his books. He's an author for Large Scale C++ Volume 1, Large Scale C++ Software Design, and Embracing Modern C++ as well. And then next after John, we'll introduce Klaus. So this is set to be a great event. Again, thank you, everybody. John, I'll hand over to you.
All right. Well, hello, everybody. I have absolutely nothing prepared. This is all going to be extemporaneous, and I will explain why a little bit later, but let me just get started. I'm also caffeinated up, so if I start talking really fast and stop making sense, my apologies. Back in 1993, I think it was, I was teaching at Columbia, and Addison Wesley at the time asked me to actually consider writing a book called Large Scale C++ Software Development. And at the time, I didn't feel that I was capable of explaining what large scale C++ software development was like because I was only 30 years old. How would you possibly know how to develop C++? Could you design it? Maybe. So I negotiated this book, Large Scale C++ Software Design. And it turns out that, it's only 850 pages. I wrote it in 3 years. And it's become quite a seller. It's in its 20th printing in many languages. And so that was how, when I went to Bloomberg back in 2001, we started designing our software. Fast forward 20 years, during the beginning of that start at Bloomberg, I started writing another book. It's actually 3 books. Large Scale C++ Volume 1 is Process and Architecture. Volume 2 is Design and Implementation, and Volume 3 is Verification and Testing. 20 years, 23 years later, 24 years later, anyway, it took me about that long, we now have this book. And this book is 1,000 pages. And this is just Volume 1. This is only the first 4 chapters of an 11-chapter book. The 3rd volume is expected in about 2 years. I wrote that first, believe it or not, and that's how to do effective testing. What's surprising is that when it comes to architecture, it's not even C++ specific, it's software specific. Everything in this book is 1998 C++. It puts footnotes in for fancier stuff, but it's all old school. I'm old school. What is it? Old gangster, That's me. Then, because I didn't want people to think I'm a dinosaur, I decided that I'd write a paper on how to use C++11. That was back in 2017. That paper was supposed to be a 7-page paper. It turned into an 11-page paper, and that turned into a 1,400-page book. And it turns out that this book is geared towards large corporations, just like the other book. The other book is an architecture book. But this book is geared to large corporations that have lots of people that may know modern C++ to varying degrees. And so if you're an old gangster like me, then you want to buy this book because it's written for me. In fact, the people who wrote it know modern C++, and it was their job to explain it to me well enough that I could explain it to somebody else. And so that's how we wrote this book. And it's broken into 3 chapters, and all of 11 and 14 are described, the language features are described in these 3 chapters. And just to annoy people, we've categorized them as safe features, conditionally safe features, and unsafe features. And people get really all bent out of shape when I tell them that the final keyword is unsafe, because they go, wait a minute, Alistair Meredith proposed override, which is a safe feature, and final at the same time. And you're saying one of them is safe and one of them isn't safe, and they're equally complex and equally easy to understand, but they're not equally useful. And in fact, one of them, final, is so unuseful that we consider it dangerous, and it has only one known use case. So that's why it's in chapter 3. The good news is that if you buy this book, you can look up each feature in 11 and 14, and it will explain what it is, valid use cases, potential pitfalls, which are those things that could be latent bugs that make it through your development process, and then you find out later, oh, I wish I hadn't done that. Either it's a runtime defect, or maybe it's a design defect, but you don't realize it. And then we have annoyances. What are annoyances? Well, they're not going to actually break anything. The compiler will catch it, or you won't be able to do it, or you'll just become annoyed because it's so painful. But they're just annoyances. So that's the way every single of the 57 feature chapters of the book are laid out. So I am both a dinosaur and an 11 and 14 modern C++ developer. But guess what? I'm also a forward thinker. So what we're working on right now are memory allocators and contracts. Contracts are something that I've been trying to do in the standard since 2012 and have been using at Bloomberg since 2004. Contracts, I should be more precise, contract checking. I've been using contracts since I was born. What's a contract? It's an agreement in software between two parties, the producer, the provider, and the consumer, the client. And basically there are two things, preconditions and essential behavior. And it's this simple. You satisfy the preconditions, I do what I say I'm going to do. You don't satisfy the preconditions, I do what I want, period. Now, what's very important is the notion of what is called a narrow contract. What is a narrow contract? A narrow contract is a contract that has preconditions. Preconditions could be on its inputs, or it could be on object state, or it could be on program state. So to make this clear, I have something like a std vector, and I use, for example, the front operator. There's no argument to it. It gives you the first data member. But if there is no first data member, then you violated a precondition. You can't call front on an empty vector. You just can't. If you do, anything could happen. What do I mean by anything? Well, the compiler is allowed to do anything. It could throw an exception. It could end the program. It could run into what's called language undefined behavior. Language undefined behavior allows all kinds of crazy stuff to happen. So we don't want to do that. Anyway, another kind of precondition is square root. Square root, you can't pass in a negative number. If you do, anything could happen. So don't do it. Now we're talking about contract checking. That is a subset of the contract that you're able to check by simply using a mechanism like assert. Now, assert is problematic because all it can do is terminate the program. But what if you could do something other than terminate the program? What if you could throw an exception? What if you could log a message and continue? What if you could do a long jump? All of these things are possible with a throwing handler. So what we are working on now for C++ 26 is a notation that allows me to specify on the declaration or in the body of a function that this thing must be true. And then based on the build mode, actually check it at runtime. And if an exception occurs, if a violation occurs, call the handler and do whatever it says. It's an extremely, extremely powerful technique. So there's something in this book called the no except specifier. The no except specifier was invented at the last minute, at the 11th hour, because we wanted move semantics in C++ 11. Move semantics require a move constructor, move assignment. And if you want that to be useful, it can't throw. Why? Because when I'm resizing a vector with a strong guarantee, if I don't know if the move constructor can throw, I have to make all my copies first. However, if I know that that doesn't need to happen. I can make my one pushback copy. And then if after that, if I've allocated the new block of memory and if I've allocated the new element, I can move all the elements over knowing that they won't throw. I've committed and I know that I'm going to be safe. So a move constructor that isn't no except, you can't use it. So there's one and only one reason in C++, it turns out. One, and that is if you have a move constructor that has a wide contract, and that's the only contract that makes any sense for move, then you can put no except on it. Every other use of no except is either wrong or unnecessary. People will give you all kinds of reasons for why this is not true, but I don't care. There's something called the Lakos rule. I didn't name it. The Lakos rule says that narrow contracts and no except are inherently incompatible. That is not an opinion. That is a fact. And has nothing to do with contract checking, and it has nothing to do with verifying that verifying a negative test, which means that if I call a function out of contract, that I can easily test it by installing a throwing test handler, calling it out of contract and catching it and observing, yes, in fact, my mistake was caught in a test build. None of that applies, because what really is true is that you want narrow contracts to stay narrow. And if you put no except on it, they immediately become wide, because the definition of a narrow contract is there's at least one combination of inputs and state for which the behavior has no requirements. That's undefined behavior. As soon as you put no except on the function, you've stated that for all inputs, syntactically valid inputs, there is defined behavior. And that defined behavior is it does not throw. Hence, it is no longer a narrow contract. It's a wide contract. It's permanently a wide contract, and you no longer have the luxury of in a checked build throwing, which means you can't check your checks, and you can't extend your narrow contract to something else. In C++, we have a bracket operator. We also have an at function for vector. They're the same, except that the bracket operator has undefined behavior when you call it out of contract, meaning that the index is too large. And the add operator, that function, guarantees that it will throw. The bracket operator is a narrow contract, and the add operator is a wide contract. The add function, call it an add operator, looks like an operator. But you know what? You don't need an add operator. What you need is a implementation of the bracket operator that in a checked build mode checks it, and in an unchecked build mode, you don't pay for the overhead. Period. Done. Because no one in their right mind would ever deliberately call the add operator out of contract. It's a bug. So use the bracket operator, turn on checking, catch your bugs, and then when you know your program is sound, maybe you turn it off, it runs a little faster. So what I've been doing for the past 10 days, there is a movement afoot in the standards committee to take what is known as the Lakos rule and remove it, because we can check things other ways, John. We don't need to use your style of negative testing, and you don't put that on other people. Well, it turns out no, has nothing to do with that. It has to do with software engineering and extensibility. And what it means is that imagine you have, and this is derived from what's called Liskov substitution, not to be confused with design by contract. Liskov substitution means I have, and I'm going to explain it in terms of versions. I have a version of software, and everybody writes, call it the standard. Call it the C++ 11 standard. Everybody writes software to the C++ 11 standard. Then I come up with the C++ 14 standard. We want the C++ 14 standard to be Liskov substitutable for the 11 standard. What do I mean by that? That means all programs that were written to the 11 standard work exactly the same way. I mean exactly. Not kind of, not sort of, not similar, exactly. Have the same behavior as they did before. But now we can write some new programs that do some new cool stuff. That is Liskov substitutability. We put no except on a narrow contract, we lose Liskov substitutability to move from the bracket operator to the at function behavior. In other words, I could have implemented the bracket operator using the at implementation, and it would be a publicly narrow contract and a wide implementation, and that would be fine. Once I put no except on it, I'm toast. So the thesis and the point of this quick talk was the Lakos rule, no except in narrow contracts, are incompatible, mostly, not totally. I mean, if you throw into a no accept, you will terminate your program, but there's no reason to do that. There is literally no reason to do that. Move is a wide contract, must be a wide contract. Therefore, put no accept on a move and call it a day. And stop being a silly person and putting no accept on everything in God's creation. Because if you do, and you happen to use exceptions for any purpose whatsoever, you increase the likelihood of bumping into a no accept boundary and terminating, which isn't safe. The other one is you're likely to be wrong, put it on too early, and thus stop yourself from backward compatibly extending your contract in the future. So again, the moral of the story is, especially for a standard, which must cater to everybody, including Bloomberg. By the way, I work at Bloomberg, forgot to mention that. Just don't do it in the standard. And then if people want to strengthen it, the implementers, if they want to strengthen it, they can always make the function no accept, because that's a compatible implementation if you want to, just can't take it back. Or you could use the new contracts facility and give people the option to do throwing handlers that catch and throw or do whatever they wanted to do. That's cool. Or you could do both, which gives people some of the functionality of both, but you can't throw through a no accept boundary. So anybody who wanted to throw and test, well, or anybody who want to throw and catch it and continue, well, it would just terminate their program, which for some people is unacceptable. So again, the bottom line is the Lakos rule, which has been in force since 2011, the paper that I'm writing, which is a mere 70 pages, which I've written in the past 10 days, basically is a short course in software engineering 101, explains everything about structural inheritance and Liskov substitution and design by contract and stronger preconditions and weaker postcondition. All of that noise gets to the point and say what we want to do is we want backward compatible software, and we don't want to stop people from doing their jobs. And that is my talk, and I am open to any questions anybody has about absolutely anything, especially software.
All right, can I ask a first question?
Please.
All right, then of course the obvious first question is, when do the other two books appear? So I have the first volume in my bookshelf. I need the other two as well.
Very fair question. So because I want to be different, because that somehow is my nature, I wrote volume 3 first, then I wrote volume 1, then I wrote volume 2, then I went back and wrote volume 1, then I rewrote volume 1, and then I published volume 1. I am a third of the way through rewriting volume 3. Volume 2 will be last, because it's about design and implementation, and I'd like to talk about things in C++ 32, and I won't be able to do that until at least C++ 29 is out. A lot of the stuff that I work on is way in the future, so if the testing stuff that I'm working on needs only C++ 11 because of move semantics, and everything else in the testing applies to anything, applies to any language or whatever, but move semantics, we need 11. So 98 requires, volume 1 requires 98, but it's the subset of C++ 23 that's 98. Volume 3 will be the subset of 23 that's 11, and volume 2 will be the subset of C++ 32 that is probably 29. I don't know, something like that. Maybe it'll be 32. But anyway, that's the idea. That's the reasoning. So the answer is 2 years for the next one, and who knows for the final one. But once you have 1 and 3, there are a lot of people out there that know how to design, implement, and I say design and implement C++. And what I would be adding there is simply categories of types, such as value semantic types, mechanisms which don't represent a value, utilities that don't instantiate, and then meta functions that really are just at compile time, and just categorizing things in very focused ways so that you have patterns, so that you can test those patterns much more efficiently. And winners focus, losers spray, and it's the same is true when it comes to writing component-based software. Does that answer the question?
Yes, thank you.
Sure.
Amazing, John. Thanks for that. Yeah, any other questions at all for John before we move on? Oh, there's one in the comments there.
Okay, I can try to look at that here.
Jeremy, I can read it out if you need me to.
Oh, if you wouldn't mind.
Yeah, of course. Regarding contracts, does this mean you see contract handlers replacing incorrect uses of no exempt? And going beyond that, would it be possible to have a contact saying this will not throw to replace no accept?
Okay, I love the question. Here we go. So does this mean that contract handlers replace incorrect use of no accept? So sadly, once you put no accept in the specification of the standard, we're lost. Can't take it back. Good news is you haven't done that yet. So even though we have no accept in places where it's not needed, it also does no harm. Now, what I'm trying to do is make darn sure that we don't regress, because if we were to regress, we would lose all this greatness that we've preserved. I will tell you that in Madrid in 2011, I scrambled to put together something that passed with high consensus because everybody was scared to death that no accept would be the disaster of all things, because nobody knew what it would do and it was there for only one purpose. So we came up with a rule that said put no accept only on wide contracts involving move, copy, and swap. And that was okay, but it was even too generous. So as it stands right now in the standard, there are no such things. We don't have to worry about it. Going beyond that, would it be possible to have a contract saying this will not throw to replace no accept? The answer to that is absolutely. So there's sort of three levels of no accept. The first level of no accept is you write something, and in the behavior, in the essential behavior, for example, imagine you had a function that says, give me an integer and I'll add 1 to it. Let me not say that. Give me an integer and I'll divide it by 2, rounding up. That has a wide contract. It'll do, no matter what you give it, it will do that for you. That will happen. So since the behavior is fully defined, this function can't throw. It cannot throw because the essential behavior already says that it's going to return. If it returns, it can't throw. So you don't need to say no accept. Take another example. Square root. Square root's not going to throw unless you call it out of contract. If you want to make that point clear, you can either say does not throw or you can say throws nothing. In either case, you have gone out of your way to make it clear that this function does not throw in contract. You said nothing about the undefined part, which is the negative value, which means if the contract is extended in the future, you might have to rewrite it to say, if the function, if the argument is non-negative, this function returns the positive square root rounded accordingly. If the argument is negative, this function throws range error. You've done that, you've made it a wide contract. It's a lot like the at function, and life is still good. But you haven't hurt anybody, because by Liskov substitution, every program that was valid using the old contract is still valid using the new contract, because they weren't allowed to call it with a negative value, and now they are. So what? Their code didn't change. Do you need to make it no accept? No accept. No accept is there only for wide move operations, period, full stop, end of story. Thank you very much. And so implementations can always strengthen it, but any standard that's designed for all people, we call it the multiverse, any such standard must not restrict or define policy. It must allow policy for the implementers and for all of its users. Anyway, I hope that answers the question. And is there another? How does C++ feature development align with Java? Now you're asking a hard question. Back in the day for my dissertation, I had to apply my rules, my Lakosian physical design rules, which are described in the 96 book, to Java. And I traded the fear of the unknown for the fear of the known. And Java is not a language that I would use simply because it's too far from the machine. But all of the principles of physical design that are in the first volume apply just as much to Java as they do to C++. As far as development goes, Java doesn't have the kind of crazy undefined behavior that C++ does. So if you're coding quickly in Java and something blows up, it's as if you have checking built in. C++, crazy stuff can happen. So for safety critical systems, you have to use a much stricter methodology. At Bloomberg, we use a methodology that's second to none and uses everything in volume 3, everything in volume 2, everything in volume 1, and it's all good. That's all I got though, because I don't develop in Java, and I will say though, the people who I've known who've gone from C++ to Java and back to C++ have a little bit of, I'm going to say, loss of detail to the machine, because they forget that they have a real machine underneath, and it takes a while to get your footing back if you forget that. It's like getting off a bicycle. You don't just get back on it. It takes a minute. Anyway, going the other way, I would just pull my hair out though, so I don't have enough to do that. Will there be any impact on low-level device development platforms? Will there be any impact? So here's the thing. No except is often used as an excuse to reduce code size. It does to some degree reduce code size. It does not, repeat, does not improve performance. None, zero, zilch, nada, no. That's fake news. That's a conspiracy theory. There's no evidence. You know where I'm coming from, or should I really tell you? So if you want to make your code smaller, a little smaller, you can put no except on things where it does no harm. Don't violate the Lakos rule, but put it on some things that does no harm. But if you're in an embedded system, you wouldn't be using exceptions at all. You would turn off the exception stuff so it becomes completely moot. So to allow for the multiverse, don't worry about it. Just don't put the exceptions on, and then embedded systems will turn off exceptions and life will be glorious. Hope that makes sense. Is that good? Are we good with that? Any more? Any follow-up? Okay. So how does C++ feature development with Rust? Now you got me. I'm not a Rust developer. I hear good things about Rust, but I am told that Rust is not the be-all and end-all for safety, that you can still do bad things in Rust if you want to, but that is only secondhand. And I have nothing bad to say about Rust. I have nothing good to say about Rust. I have nothing to say about Rust. My apologies. I'm just not a Rust developer. I'm a dinosaur. You know, I know a little Ada, I know a little Lisp, wrote in BASIC, COBOL. What is it? Yeah. What's the other one? APL. And what did I say? Did I say Pascal yet? I don't know. Bunch of those. Done a lot of that. And my favorite by far and away is C++. And before that, I wrote in C. And nothing terribly wrong with C, except that it feels like it's like putting on a straitjacket, saying I have to now code with a straitjacket on, and I prefer not. Next question. I have another question. All right, I see one more question. I don't know. I don't want to go over my time, but I'm happy to answer one more question if that works. We have ranges transform, optional T transform, and map. Okay. And we have range transform join. Oh, you're getting up there. And then the monadic bind. Okay. Is the committee embracing functional programming in the foreseeable future and have one transform for every functor, one bind for every monad? You're asking a really good question of which I have absolutely no knowledge and nothing to say. One person you might ask is David Sankel. He's very much into functional programming, and he might be able to give you a better answer to that. If you send me an email to jlakos@bloomberg.net, I can forward it to appropriate people and get you an answer. And yet it says, well, some above is in C++ 23. Yes, I think that's probably where there's some desire to abandon the Lakos rule, even though there's absolutely no need, because I think the people who are working on functional programming could care less about classical software engineering. Oh, I didn't say that. Anyway, that's not really true. That's just my caffeine talking.
Thank you very much.
Right.
Amazing. Cheers for that, John. I'm sure we could sit here and answer loads of questions, but that was really enjoyable. We're now going to move over to Klaus. You would have heard him briefly at the beginning ask the first question. I believe he's got a slide prepared for you guys, and I will leave it over to Klaus.
All right. Well, thank you, everybody. And I'm going to have to run, but have a great rest of your talk.
Thanks, John.
All right.
Bye.
Bye-bye.
Right. So thank you. Okay, you can see my slides, can you? Okay, perfect. So then, first of all, thank you very much for the introduction and the invitation. I really appreciate this, as this is the very first of these C++ series. And so I want to talk about software design as well. Apparently this is a pretty hot topic, but this is kind of expected when you invite John Lakos and me. So not as many people know me, much more know Jay Lakos, so allow me a very quick introduction. So yes, I'm talking about C++ as a profession, which sounds pretty boring, I know. But if I say that I'm working as a C++ trainer consultant, it actually doesn't sound so bad anymore. I'm even doing C++ free time. So if, for instance, I'm organizing a user group, the one in Munich, so pretty similar to what we're doing right here. And I'm also once in a while doing something for conferences like CPPCon, etc. So, and now allow me to start with a completely shameless advertising my book. I've only one book, but I've also written a book about C++ software design. So design principles and patterns for high quality software. And of course, the very first question that now everybody's asking is, why write a new book about software design principles and design patterns? Are there enough? Is this just something that you've covered in the last 20 years already? Of course, most of you probably think about this book. The book on design patterns, it's in the title already. And I would say it's really the reference on software design. This is what we call the Gang of Four book, published in 1994, 1995, so it was late in 1994. And it really is the reference for 23 of the most commonly used design patterns. Now, pretty much all of the patterns that most people know are in that book. However, also, almost all the patterns in this book are based on inheritance. This is what this book does. It's in the subtitle, Elements of Reusable Object-Oriented Software. And so indeed, it's a good question. Why write another book about software design and design principles? Well, for me, there were indeed 4 good reasons. Reason number 1, too many developers don't think enough about software design. This is something that I see again and again when I do my training classes, when I do consulting. And so this is what I would like to talk about shortly. Then, too many developers believe design patterns are object-oriented programming. That's definitely something I want to communicate. This is definitely not true. And third, too many developers still use inheritance by default. Also something that we don't really do anymore in modern C++. And that's actually a 4th reason. Too many developers still don't know their patterns. So the last point is what I still cannot do here. So if this is interesting, please contact me personally. But I want to give you a little bit of an idea about the other 3 points. And so let's first talk about why too many developers don't think enough about software design. So in the software community, in the C++ community specifically, we have this tendency to think about the little details, the nifty little implementation details. So if you go to a conference, I would say that far beyond 60%, even 70% of talks are about features, about C++ standards, about nice little implementation details. If you're looking for talks on software design, you'll find very few. There are people that talk about this, absolutely. But given that software design is pretty important, there are very few people. Some people still think about the next neighbors, the things that communicate with this little piece, but very few people indeed think about the big picture. All the connections, about the real design, about the architecture of some product. And this is indeed what I see in my training courses. Hardly anybody has a software package, software framework, whatever, that, for instance, uses architectural decision records or has an architecture description at all. And so that's what I'd like to change a little bit. That was one of the reasons to write the book. So, quote from the book: design plays a much more central role in the success of a project than any feature could do. Good software is not primarily about the proper use of any feature, rather it's about solid architecture and design. So good software design can tolerate some bad implementation decisions, but bad software design cannot be saved by the right use of features, old or new alone. So I just feel this is a topic that is vastly underrepresented in our community. But as a second point, too many developers still believe that design patterns are OOP, so object-oriented programming. And again, not a big surprise, because the good old book, as I said before, has this in the subtitle, object-oriented software. And so, of course, you do remember design patterns like the strategy design pattern. This is one of these patterns from the book. And yes, it uses inheritance. And yes, it definitely looks like this needs inheritance hierarchies and classes, etc. But there's a very basic idea about this design pattern. So some context with some function allows you to inject the behavior from the outside. So that the context has a strategy, that this context is given a strategy from outside. This is what we usually refer to as dependency injection. That pretty much is the basic idea of the strategy design pattern. This is used in many, many more places than you would believe. Consider, for instance, the standard library. Now, if you take a look at the standard library, there are hardly any base classes. But there are many, many uses of the strategy design pattern. For instance, the unique pointer. Unique pointer uses the strategy design pattern. It's not immediately obvious, perhaps, but you know that a unique pointer takes a deleter. And that is dependency injection. So you are able to customize the use of unique pointer by just passing how the unique pointer should delete the pointer. You're in charge, not the unique pointer. It's a strategy. This, of course, the same idea is true for pretty much every single container, vector and list and unordered sets. All of them allow you to customize the allocator. And that's the same idea. You inject how exactly the memory should be acquired. All of these are strategies. And of course, unordered set even has a couple more options for you to customize things. And to make things even better, accumulate is one of many, many algorithms in the standard library, allows you to customize behavior. That means of the fourth parameter. So you yourself specify whether you're going to use plus or multiplication, any logical combination. You set this reduction operation. All of this is strategies. So from this perspective, none of them are object-oriented uses of strategy, but there are hundreds of examples in the standard library alone. So from my point of view, this is an absolutely fascinating detail. I believe design patterns are pretty much everywhere. Everywhere where you look, throughout the standard library in your code, design patterns truly are everywhere. It just might not be object-oriented in the traditional form. All right, but then there's the third point. Junior metadata loaders still use inheritance by default, which I believe is not a bad thing per se. It's just not exactly what we're doing today anymore. So let me give you an example where I believe it's a really, really fascinating, beautiful, modern way of doing things without using inheritance. And so, first of all, you might remember this talk from 2013, Inheritance is the base class of you. A funny title, it really is. Kind of a nice choice of words. But this was not really a talk that was supposed to be fun. It really was to communicate to the community, inheritance is not always the right choice. Or to say it in the words of the pragmatic programmers, it rarely is the right answer. So my example is the visitor design pattern. And I know the complexity of this pattern alone slays you. It's one of the more complex forms of design patterns in the book. However, very short reminder, the idea of the visitor pattern is to separate pretty much all the functionality out of a class. So if you consider some shape hierarchy, shape being a base class, and then circles, squares, and other kinds of shapes being derived classes, then what you don't want to have in the shape class are the operations. Because you might want to add operations often and frequently. And this is where this visitor design pattern steps in. You extract this knowledge in form of this shape visitor base class, which now represents operations on shapes. And by just isolating this, essentially by following the single responsibility principle, you're suddenly able to easily add new operations. Rotate, draw, any operation that you have in mind, easily, just adding new code. It's a fantastic pattern as such. However, every design pattern, every single one has some advantages, but unfortunately also some disadvantages. And so in this context, Well, I'm now suddenly able to add new operations on the left-hand side easily by just writing new code, new base class, new derived classes. I cannot easily add types on the right-hand side anymore, because this would pretty much require me to change everything in the code base, or at least on the left-hand side. Now, adding a triangle here would require to add a virtual function there. It would have an impact on all the derived classes. And this is again the architecture thing. In this little example here, it's not a big thing. But if you think big, now 150 developers in a 10 million line project, this might actually have a huge impact and might not be something that it can do anymore. So it's a great pattern for a specific use case. However, the classic form that you see right now usually comes with a couple of disadvantages. So this 1994 visitor solution, first of all, requires two inheritance hierarchies. The left-hand side shape visitor hierarchy and the right-hand side shape hierarchy. We have a lot of virtual functions, which makes us as C++ developers kind of sad. We love performance. It's a very performance-driven language, and virtual functions are just not as fast as other approaches. It likely performs many allocations. That's just because we allocate with the operations, but also the shapes and allocations themselves are expensive. Of course, we also have fragmented the memory because of that, another performance disadvantage. And lastly, many pointers floating around. Pointers, this takes an hour at least to show, are usually making life miserable. So this is not what we're doing anymore in modern C++. So what do we do instead? Well, a breathtakingly beautiful and simple solution indeed. So let me show this in code. So let's start with a circle class. It's just a circle. You don't see any base class, you don't see any virtual functions, just the most simple kind of circle that you could possibly imagine. There's nothing special about the circle. It's totally decoupled also, which is beautiful from an architecture point of view. Then, of course, there's not just circles, there's squares, rectangles, triangles, whatever you want, but they're all very simple, don't require any base classes. And of course, we have operations like draw. This is, of course, the stuff that works on circles and squares, which you now want to treat polymorphically. This is what you today just do by means of std variant. Std variant, in this example, stores either circle or square. But that represents an abstraction that I would call a shape. It can be any kind of shape, contain any kind of shape. And so it pretty much plays the role of a base class in this context. So in order to draw shapes, I could traverse a vector of shape values. I could simply call std_visit, which is a pretty simple thing to do. And so in the main function, I could create an empty vector of shapes first. Shapes being just an abbreviation for vector of shape. And I could push back different objects, circles, squares, all different kinds of shapes. There's no new, there's no make unique or anything similar. It's values that we put into the vector together, which is breathtakingly simple and also breathtakingly beautiful, just of the simplicity. But also, this was it. This was the little example. You've not seen any base class. You've not seen any pointer. You've not seen any manual allocation. There's no inheritance. But it has pretty much exactly the properties of a visitor design pattern. Why? Well, going back here, because you can easily add operations, draw, serialize, rotate, whatever you're thinking of. This is super easy. It's just writing about new code. But it's kind of difficult to introduce new types, new shape types. You would have to change the variant. While this may be perhaps a little more streamlined, a little simpler than in a traditional approach, it still is an intrusive change. Same properties as with a classic pattern. So to summarize, this rather value-based solution requires no base classes, there's no virtual functions, performs no manual allocations. I said manual inside the vector we do, but we manually don't do. We don't use any pointers anymore. Everything is values. The solution is much shorter than an original solution would have been. It's, I believe, super easy to understand. There's nothing really complicated here. And additionally, it's significantly faster. Of course, as soon as you mention faster, people's eyes are widening. After all, it's C++, and people demand some kind of proof. Okay, performance. Now, this is probably the difficult part of this entire presentation, because performance values, of course, depend. And so, I'll show you a couple of performance values. If you promise me that you will not take this too serious. So, do you promise me to take these results not too seriously and really just consider them as qualitative results? Do you promise? Okay, I'll take this as a yes. Yes, you have to. There is no way around that. So, just a couple of numbers from my system, which uses 4 different kinds of shapes. That's it. But I generate 10,000 randomly generated shapes, run 25,000 translate operations on each, which means the operation is the same on each on each kind of shape, doesn't matter. I use 2 compilers. The results are a little older, but now the compilers, there's new compilers. And it's a standard Core i7 with 3.8 gigahertz. So the classic visitor that I did not show explicitly, but that runs approximately in this speed. Okay, that's a number. It's a baseline. If you now switch to variant, then it's already significantly faster. It's not just 1, 2, 3% faster. No. We're talking about 20, 25% here, and this is a major improvement usually. Seriously, if you improve the performance of your code by 25%, you are employee of the month. Seriously. And not just for 1 month, for many months. Yeah, so this is huge. And there is, so this was older compilers. Things have changed a little bit. But at the time, I also used the version from Michael Park called npark variant, which you'll find at GitHub, which was actually even faster, especially on the client compiler. It's a huge performance difference, huge improvement. This is great. However, as a last remark, please also promise me that you do not, because it's so fast now, switch everything and pretty much every inheritance hierarchy to variant. That's not the point again. Variant is, after all, a visitor. So you will certainly have a little more trouble to extend the types. It serves a specific purpose. It's not a good for all pattern. All right. So why should you care about software design? Well, because I believe software design is essential for the success of a project. It really is. It really matters. It's not just the implementation details. And every software developer is also a software designer. So you design the software. Yeah, every developer should also be some kind of architect. And design patterns are everywhere. You use them on a daily basis, pretty much everywhere. They might not look like the original ones, but you use them. Then design patterns are not just OOP, inheritance based. They have a much wider use case. And last but not least, they're very different today. So, of course, it definitely helps to bring yourself up to date a little bit. All right, that's it. Of course, I'm super happy if you have any questions.
I have a question.
Please.
Yeah. Well, at the beginning of your talk, you said design patterns are like language-wide, cross-language. But what about the fact that in some languages they just kind of disappear? Like think of any Lisp dialects closure or even Haskell function surfaced class citizens, and so the strategy pattern is kind of, what's the point of even giving a name to it if it just means passing functions around? And C++ has lambdas and stud function. I mean, modulo its weaknesses, but it kind of goes in that direction. And now maybe strategy is the easiest to call useless with respect to the others. But what are your thoughts about this?
This is actually a super point. This means that some languages actually made these felt that these patterns are so important that they're built into the language. So I believe it's proof how important they truly are. If a language makes them first-class citizens in the sense of you can really implement this, it's already there. It's a proof that this is really important. But of course, it is a little different in every language. C++ is the language that is most manual in this regard. Other languages have acquired these patterns afterwards and make them much easier to use. Yeah, this is part of the language.
So I have a follow-up question. Oh, yes. Sorry. Go ahead.
No, I just wanted to say you're correct. I just feel that this is not an argument to say we don't need to know about them anymore because the language does not take care of this. I still believe you should have a little bit of an idea which advantage and disadvantage to gain from each pattern. This will definitely help, especially if you switch languages, of course. But please follow up.
What about the risk of, like, in teaching design patterns, there's a risk in people absorbing them as they are and start using them without actually thinking about what if they actually need them, especially in considering what the language offers, like C++ design patterns. If you search design pattern, strategy pattern, C++, you would find classes, probably even in inheritance, but mostly classes with operator, call operator. And somebody could just tell the people who tries to do that, hey, you have lambdas, use lambda. Don't mess around with classes. Don't you think that teaching design patterns so structurally could actually be counterproductive in these terms?
I think so. That's why I teach them differently. But I think this will take time. It absolutely will take time to adopt this a little bit. We are still in the phase where we teach them very object-oriented. Unfortunately, now this is still a very, very strong idea. There's still people that believe C++ is an object-oriented programming language only. Yeah, so they don't realize that it's really multi-paradigm. Before John Lakos was asked a question about function programming, I believe we embrace this more and more because there is so much to gain from it. So we'll have to adopt how we teach them, how we talk about them. Definitely, yeah, I agree with you.
Yeah, that was me, the one who asked the question to Lakos. So
okay,
it's not a coincidence.
No, this was a seriously good question. So to give my answer to this, we embrace this because functional programming has a lot of advantages, a lot. However, it's not the one paradigm. That I would say is never true. Object programming has advantages, function programming has advantages, generic programming has advantages. What we now need to learn a little bit, what we should talk more about is what are the advantages? Why should you use, which paradigm should we use when? Okay.
Thanks.
All right.
There are a few more questions in the chat, Klaus, I think. Can you see them?
I have to. So how is std_visit generally implemented in standard library? Of course, there's not one implementation. No, there are many implementations. But what is generally done is a switch statement. This is kind of a very simple solution, but it works. And it's pretty fast. So the standard visit function will probably have 32 to 128 switch cases, and it will dispatch to the according type. Beyond that, because it still must work, what they use is some kind of array of function pointers. So a slightly indirect dispatch, which is fine. It's a little slower, but it definitely works for any number of types that you pass. So in the end, it's nothing but a good old switch. Yes. All right. Processor architecture can affect best practice. Definitely a little bit. I agree. But I would see the patterns a little independent of how we truly implement stuff later. So it does have an influence if you think about performance, etc. But I usually tend to see design and architecture a little independently first, and then later when you do the implementation, suddenly it definitely makes a lot of impact, of course. All right. Now, slightly longer question. Do you believe government regulation design patterns is necessary, especially for the mitigation of modern threats like misinformation, bias, and algorithmic development? Definitely difficult question. I've never thought about this. So I do know that there is some government regulation currently in the US, not about design patterns, but they're trying to streamline software development as a whole a little bit. Because we have a lot of problems, a lot of cowboy mentality when we write software. Not a lot of tests, not a lot of design around that. This is what currently is happening. You know, we try to improve software quality by doing some kind of regulation. I've not heard about anything to regulate design patterns. I don't know if this can be done. So I've not thought about it, sorry. Okay. Should you have a design similar to hardware approach data and control plane, which I feel is also basis for the functional programming? Okay. Also something that I've not thought about before. But the second part of the question, what do you think about nano and microservices? That's something that I can answer. Microservices is a great tool, but it's not the ultimate tool. So just for your reference, Amazon, for instance, has changed back from microservices to a more monolithic approach again, because it works better for them. So it's a great thing, but it's not the ultimate architectural pattern for everyone, apparently. In the end, it all depends. Okay, and how can you determine what design pattern is best for a software solution? That is a difficult thing. It always is. I never said it's easy, but it's something that definitely you have to practice a little bit. This is why I wrote the book. This is what I tried to teach, to communicate a little bit. But in the end, perhaps it's also a little bit of trial and error. Try to pick the first thing that comes to mind, the first thing that seems to fit. And if it doesn't work, then evaluate why it didn't work and look for the thing that more closely fits the needs that you later discovered. Okay, and as design patterns are not about OOP, then I assume design patterns can be compatible with data-oriented design. Absolutely. Data-oriented design is just another way of organizing the data, working on the data, and definitely there are patterns that it can apply as well. I don't see why a strategy would not work in a data-oriented setting, but there may be a couple of special patterns for that too. Okay, so I think this was all the questions. So Pippa, back to you.
Thank you so much, Klaus. That was great. So yeah, we're now going to speak to Allan Jones, who's also prepared a slideshow, and he's a C++ software expert currently working at Invent Design Build, and he'll be talking about using the Qt framework for embedded systems. So Allan, when you're ready, thank you.
Right. I'm vaguely visible there, right there. Okay, hello everybody. So I'm going to talk a little bit about the use of the Qt framework, particularly with respect to embedded systems. Often people associate Qt with as a GUI framework, but it has a lot of features which are quite useful for embedded developers. So. You got a slide there?
Yeah, we can see it.
Ah, super, right. So that's me, Allan Jones. I've worked with C++ since the mid-90s. A lot of my work has been in things like marine navigation and surveillance systems. And now I'm focused mainly on embedded systems, IoT, and particularly robotics, and particularly robots that either float or swim. I first came across the Qt framework in 2013, which was its use in a long endurance autonomous marine vehicle. So definitely an embedded rather than a desktop type of application. So a quick overview. I'm going to sort of quickly describe embedded systems that as applied to this talk. A little introduction to the Qt framework. If people are already familiar with it, then there's probably a bit of familiar ground, but I will try and highlight the features that are of use in an embedded system rather than the more general description of it. And then a little bit of a discussion of the downsides and the trade-offs of whether to employ Qt in a design or not, and a little description of some of the alternatives. So embedded systems, for the purposes of this talk, we're talking about small, generally Linux-based systems with a limited or no UI, or UI that's composed of lights and switches rather than a screen particularly. Interfacing to hardware for the purposes of controlling or monitoring something, and sometimes fairly limited processing power. Not talking about bare metal real-time operating systems or microcontrollers in this, and also not talking about kind of desktop applications. So I think the key thing is that it's something that's probably a Linux-based system, and it's talking to hardware. So a little background on the Qt framework. So essentially, it's a bunch of libraries and a preprocessor for C++. That's a gross oversimplification, but that'll do for now. So it started, I think the project started around about the end of the 90s, and Qt has gone through an interesting and checkered commercial history, but seems to be quite strong and certainly as both I think commercially and technically in quite a strong position. So it comprises a number of modules. The only compulsory one is Qt Core, which contains the meta object stuff, concurrency, threading, and event part of it, which we'll talk a little bit about. There are also a large number of optional components. The most obvious one, I guess, is the GUI widgets, which lets you design nice desktop GUIs. There's quite a comprehensive networking package, multimedia, etc., etc. There's also the preprocessor, which generates what is best described as C++ magic to do some of the additional things that Qt adds to C++. So it's a large framework, and a lot of it's not really relevant to embedded developers. So as I said at the start, people usually think of it Qt. Oh, that's a thing for drawing widgets and making GUIs, but there's actually an enormous amount more to it than that. So I'll do just a very quick hello world, not even including the hello world part, just as a sort of to give an idea of what a basic Qt program looks like. Have you got that screen? Okay.
Yeah, all good.
Okay, good. Okay, so I mean, in its sort of minimal case for an embedded rather than a GUI application, the key parts are a core application object, some of your own business logic, whatever you want to have, and then the program will sit running the event loop in the exec function until either a signal like Control-C or a Qt quit message tells it to stop. So that's kind of about the simplest Qt program. So going on from that, I'll just take that example and show a little bit more of the functionality. So classes derived from QObject, which is the main base class. It's not the base class of everything in Qt, but it's the most significant base class and provides a lot of the more interesting functionality. So in this example, we'll just override the event loop, the timer event, and this makes use of Qt's event loop. So in the class that I've created here, we've derived from QObject. There's a piece of Qt magic in the form of that macro, and then there's a timer event which we've overridden, and so we start a timer, and lo and behold, the timer gets called. It's not super interesting, but one thing which is quite interesting is that that the timer event is being called on the same thread as the constructor was called on, or as the start timer was called on. So already you've got something which is quite nice. It's very easy to set up a timer and get your calls in the same thread context. So you don't need to do any mutexes or stirred atomic or anything on the variables that you use within here. So the signal and slot mechanism, I guess, is the kind of key part of the Qt framework, and it's a way of connecting objects together and allowing them to communicate with each other. A signal is emitted by an object, and when we talk about signals, we're not talking about unit signals. Qt signals are their own very different thing. So a signal is emitted by an object when something happens, and a slot is called in response to that signal. So the basic syntax is that when something happens in the button object that causes it to emit clicked, then some other object is called on its do something function. So very simply, I've made two objects, an instance of main class and an instance of other class, connected send update from one of them to handle update of the other one. And more Qt magic. So now we have a new section within the class for signals, which is something which is understood by the Qt preprocessor. And so within a timer tick, we're just emitting the send update. Within the main class, again, we've got a new section within C++ where we can declare slots. And in the main, we've connected the signal of one to the slot of the other. And when we run it, a signal from other class calls handle update in this class. So that's nice, but again, it kind of leads on to something which is again a bit more interesting, particularly in the embedded world, that we can actually connect signals and slots asynchronously. So we can make safe connections between threads, and we can send whatever data types we like between two different threads. So exactly the same syntax with two classes. We connect the signal from one to the slot in the other one, but this time when we send the signal, when we emit the signal, we're emitting it not from the main thread. I've just set up a separate worker thread to emit the signal. within the main class, the code is pretty much the same. The only slight difference is here that we're sending a stud string, just to demonstrate the fact that you can send whatever custom types you like. If it's the type not recognized by Qt, then you just need to register it. But when you run that, the interesting thing is that the updates are sent on this thread, but they're arriving in the context of the main thread at the other object. So again, we've got a nice mechanism through the event loop of connecting together two different threads. Qt has its own form of memory management, which is kind of both a blessing and a curse. Anything derived from Q object has the option of taking a parent, and when the owner of a class is deleted, so anything that belongs to it is also deleted. So you can make a hierarchy of objects, and when the bottom of that hierarchy, or top, whichever way you look at it, is deleted, it will systematically delete anything that it owns. So as I mentioned at the start, there are quite a lot of libraries within Qt, quite a lot of utilities. So for embedded development, things like serial port and networking and Modbus are all really quite useful. And something like serial port is particularly convenient because you don't have to worry about blocking calls, because it has a signal which will be emitted when data arrives. So the serial port thread will block, but it'll emit data to you to your thread when data arrives. They're also because Qt is quite a large project, there are also quite a lot of people developing third-party libraries for it. One of the utility classes, which I've just mentioned sort of briefly, is QStateMachine, which makes it very easy to manage explicitly states within a system, which is something that we're doing all the time in embedded systems. So as a wee code snippet, you can set up derived classes from QStateMachine to do your business logic in, and then you can set up explicitly the transforms between them. So this is initialization state will move into operating state when initialization complete is emitted. It'll move into fault state when a fault state is emitted. Similarly, the fault state itself doesn't have any transition, so once the system goes into fault state, then it's game over. And so for example here, if the system's in the idle state, if the controller emits switch to operating, then the state becomes operating state. So you can very explicitly lay out the state of a system, and states can have substates within them. So the calibrating state might have several states that it goes through before it completes the calibration. So that's one of the really useful, particularly in the embedded world where we're always dealing with states and state transitions. So the Qt framework plays quite well with other frameworks and other libraries. I've used it quite extensively with the robot operating system, and Qt integrates very nicely into ROS's top-level theme-8 lists, and you can do things like manage the startup and shutdown of the system and simplify the message handling, as well as making use of things like serial port and the networking libraries. So to add Qt into a ROS project, I think there are just one or two things that needed to be added to the make list. So it's really not a particularly onerous or difficult thing to do. So it's essentially finding the packages, setting up the preprocessor and just linking with the Qt core library. And here's a little example of the startup code. So create a worker thread and a robot object, and then when the thread starts, it tells the worker to go to run its process function. When the worker finishes, it tells the thread to quit, etc., etc. So it's the signals and slots mechanism makes for quite a nice startup and shutdown. And within within the actual logic of the robot, you can make use of the timer. So here's a sort of pseudocode class which initializes the robot operating system and starts the timer. And within the timer, it spins spin once runs the event loop of the robot operating system. If Ross wants to quit, then we just kill the timer and emit finished, and we're back on the previous function, and the system shuts down. It can also use the mechanism to move data onto the main thread, so the process will be running on a worker thread, and it just posts data back to be handled on the main thread. So again, it's just a neat way of simplifying some of the code. So it's kind of summary in a way. Qt can simplify the development, particularly useful around blocking calls, things like serial ports and net TCP/IP sockets. It's quite useful for memory management. You can do safe thread connection, and threads will disconnect. Signals and slots will disconnect safely when an object's deleted. So it's not like a callback where if the callee is deleted, then the system's going to crash. And it provides a whole range of utilities for hardware and sort of network interaction, and it integrates well with other frameworks and libraries. Downsides, it's an extra dependency, so when you're building Yocto, you've got to add it in or and make sure that you ship the right versions, etc. It's reasonably large. Qt core is 6.8 megs, I think. So, but if you're running a lot of other stuff, if you're running ROS, for example, then that's probably not a significant size. It definitely has its own way of doing things, which are somewhat different to standard C++ practice. It makes use of a number of macros for the preprocessor. The memory management scheme is probably different to how most people would do memory management, and if you're using static code checkers, they'll get quite upset at some of the things that you need to do in Qt code. Because it developed kind of in parallel with C++ and predates C++ 11, there's quite a lot of duplication of things like collection classes, and it has its own coding style which might clash with people's own style. Licensing issues. There is a commercial license available, but it's certainly not cheap. If you're General Motors, it's fine. If you're a small company, it is quite significant. The libraries are also available as LGPL version 3, so you have the option that you can make your code open source and license your own code as LGPL v3. Or in commercial products, you can, strictly business-to-business projects, you can dynamically link to the Qt libraries and keep your code closed. In consumer projects, then you need to provide the ability for the user to replace the Qt libraries, which I guess people are probably not going to want to do. So that's almost a bar on the use of Qt in consumer products. And the definition of consumer products is kind of anything which a family might own or might be incorporated or used within a dwelling. So if you develop a product for a hospital, for example, that's fine. But then if you decide that you want to have outpatients have access to that product and they want to take it home, then suddenly you have a product which is used within a dwelling and you fall foul of the license. There are a number of alternatives. There's a project called Copperspice, which is an open source fork of Qt. It's a major undertaking, and I suspect that it doesn't have the backing that it really needs. I'd be reluctant to make use of Copperspice in a project just because it doesn't have it's not as widely used, and I wonder about its long-term viability. There are a number of alternatives for things like the signal and slot mechanism, but none of them kind of tick all the boxes as far as I'm concerned. They either don't have good cross-threading support, or they don't handle custom classes well, or they don't have that you can't create timers easily. So there are none that I've come across that have made me think that they would be a viable alternative most of the time. So just in conclusion, the Qt framework, certainly I found it useful in embedded development, and simplify and reduce development time. It's a one-stop shop. There are lots of libraries available for connecting to serial ports or networking, but Qt provides all of it. It's all extremely well documented, and it all plays together very well. The signal slot mechanism can be a bit difficult to debug and adds another level of complexity in terms of interaction between objects. So objects don't just call each other directly, but they might have signal slot relationships. And if you're considering using Qt for a project, then be aware of the licensing issues. Right. Thanks very much.
Great, thank you for that, Alan. We do have a few questions in the chat for you. Are you able to see those, or would you like me to read them out?
Yeah, no, I've got them here. Yeah.
Great.
Yeah, so the first one, how to use a signal slot mechanism in a multi-threaded environment. Well, I guess there are two reasons for multi-threading, I suppose. One is for performance, and the other, which happens a lot in the embedded world, is that you've got some call which is blocking. So the mechanism works in that you generally Qt will automatically decide whether the call is to the same thread or to a different thread. If the call is being made to the same thread, then it's just that then the mechanism is exactly the same as a callback. It's a direct call to that function. If the emitter and the receiving slot are on different threads, then Qt will put the data onto the message loop, and then the message loop will dispatch that to the callee. Oh, thanks, have to leave now, right? Okay. Yeah, what are the C++ entities used to implement custom memory management? I guess raw stroke shared pointer. That's a good question. I don't actually know. I think that there is a little bit more to the destruction of objects, because one of the things that Qt does when you delete an object is that you have to make sure that it's disconnected from any signal slot relationships. So I think that the memory management mechanism is a little bit more complicated than just a smart pointer. If you want to explicitly delete a Qt object, there is a call, or I should say there's a signal, which is delete later. So if you emit delete later and that's caught by an object, then it'll complete what it's doing in that call, and then there is some mechanism, which I have no idea how it works, will delete the object once it's freed from the message loop. Should you use QML for embedded touchscreens instead of QWidget? Yes, QML. I think the answer to that is two things. One, it kind of depends on the application. QWidget is very simple and very quite quick to use, but QML is quite nice. I think one of the things which QWidgets doesn't do well is multiple touches. It's fine if you've got a resistive screen and you've only got one touch. So you've got a kiosk in some industrial or marine environment where you've got a resistive screen because people are using gloves and it's all covered in seawater. If you want to use more sophisticated gestures, then QML is nice. And I must admit, I haven't used QML very much. I've used it to a certain extent, but I think I would definitely look at it as a solution, particularly if you want to make a really nice kiosk. I think that would definitely be something worth looking at. And the Qt organization are putting a lot of emphasis on it. So I imagine that a lot of car entertainment information dashboard systems probably are QML. Embedded. Yeah, so one of the biggest limitations for embedded programs is the lack of dynamic memory. How does Qt cope with this issue? Well, it doesn't at all. If you're in I suspect this is more on the sort of microcontroller side. So if you're running Qt, then you're running something which is at least running a cut down Linux, and so there are memory restrictions, but not to the extent that there would be in a real limited situation like on a microcontroller. Anyone have any more?
Okay, is that the last of the questions, everyone? Okay then, great. Well, yeah, thank you very much for that, Alan. And yeah, big thanks to all the speakers, Klaus as well, and to John. Yeah, and thank you for everyone that attended as well. We hope it's been a good event. We hope everyone has taken something from this. I am not technical at all. I've never written a bit of code in my life, and even I feel as though I've learned something from this, even if it is just how complicated C++ is. So yeah, thanks all for attending. We've been hosting a few of these events across different programming languages for the past few years now, so we really wanted to start one for the C++ community, as we are, recruiters in this space, and it's just another way that we can add value to that community. We are going to be planning one for July, I think. We do have a few speakers lined up already, just waiting to get the date confirmed. But yeah, watch this space. Should be looking towards the end of July for the next event. As always, we really appreciate your feedback. So if there are any topics, concepts, or speakers that you'd like to hear about, then please do let us know. Either drop myself or Sammy or Pippa or Charlie a direct message, or you can leave a comment in the events page as well, if or in the chat, on the Zoom chat as well, if there are any particular topics or concepts you'd like to hear about future events. Eventually we may also look to host face-to-face meetups, which we currently do for our JavaScript and .NET meetups. So yeah, after a couple more virtual events, we may consider doing some face-to-face ones as well, which will be a great opportunity for you guys to network. So yeah, if you want to keep up to date with the future meetups, please do follow the IO Associates LinkedIn page. You can, we will update you with the next C++ meetup, but also if you want to check out the other meetups that we host, again across other programming languages, then you can you can get updated from there. So yeah, thank you everyone for attending. It's been a great event. Thanks again to all the speakers, and we look forward to seeing you at the next one.